I want to talk about the concept of effective nuclear charge, which is usually the term applied to how much of the nucleus a valence electron sees. So for instance, if we look at a sodium atom, it has 11 positive charges in that nucleus, but the valence electron, which I've indicated in red here, doesn't see a charge of plus 11 because there are electrons between that negatively charged nucleus, that negatively charged valence electron and that positively charged nucleus that interfere or screen the nucleus from valence electron. So in the case of sodium, there is one valence electron. We've got 11 protons in the middle, but we've got 10 what we call inner shell electrons, electrons that are closer to the nucleus than the valence electron, blocking the positive charge from the valence electron. And what we say, and this is only an approximation, it's not an exact number, but we say that approximately the valence electron sees the plus 11 charge in the nucleus minus the 10 inner shell electrons for a total charge or effective nuclear charge of 1. In magnesium, what we're going to see is something slightly different. Magnesium has 12 protons in the middle, and the other concept we need to accept, and we're not going to explain exactly why it is today, is that electrons in the same n level or the same shell don't screen each other. So this valence electron and this valence electron, to a first approximation, it's certainly not 100% true, but to a first approximation and close enough for what we're going to talk about today, don't shield each other. So in magnesium, there are still 10 inner shell electrons, but each valence electron is screened by those 10 valence electrons and sees 12 positive charges of the nucleus minus the 10 screening electrons, or an effective nuclear charge of 2. One more than for magnesium. If we apply the same logic for aluminum, there are still only 10 inner shell electrons doing the screening, and it's only the inner shell electrons that do the screening. There are 13 protons in the nucleus, so each valence electron feels approximately 13 minus 10, or 3 nuclear charge. Now, you'll notice, as we go across the periodic table from sodium to magnesium to aluminum to silicon and so on, the effective nuclear charge goes up because we have the same number of screening electrons or inner shell electrons, but we get more and more protons as we go from left to right across the periodic table. What this means is, as we go from left to right across the periodic table, the electrons tend to be held more tightly. It's harder to lose them. And we've seen this before in some of the chemical reactions of these elements. Sodium has a very easy time losing this one valence electron compared to magnesium or aluminum because it feels a smaller effective nuclear charge and is held less tightly. In terms of going up or down the periodic table and how tightly electrons are held, it's not the effective nuclear charge we look at, it's actually the radius. If we compare sodium to lithium, both in the same column, both we would calculate would have approximately equivalent effective nuclear charge, but the outer electron, the valence electron for lithium, is much closer to the nucleus than it is for sodium because the valence n level is 1 smaller. That means the electron is closer to the center of positive charge. That means it's held more tightly. The sodium's valence electron, further away from the center of positive charge, is held less tightly.